do Newton's second law of motion. All right, so basically acceleration, and as I've stated in previous lectures, acceleration is due to the fact that when you add up all the forces that are acting on an object, that if there is some leftover force pointing in any direction, there's going to be acceleration in the direction of that force. A good example would be if you have a table and you rest a bottle on top of the table, the bottle isn't going to go anywhere. That is because the force of gravity is pulling the object down, and the table, its contact force, also known as the normal force, is pushing up. So these two vectors perfectly cancel each other out. But if you were to remove the table, then you take away that normal force, and now you have the force of gravity acting on the object. So that force is going to cause the object to accelerate downwards. There's all kinds of different forces. There's the force of friction is an example. So if you push a real object along a table, it's not going to be perfectly easy to move it. Now, some objects are easier to move, like if you had a block of ice and you're pushing another block of ice along, it's going to move really easily. There's not going to be a lot of friction. But if you had, like, say, a metal block with sandpaper on the bottom and you try to push it, across some wood, it's not gonna. There's gonna be a lot of friction because of the stickiness due to the imperfections of the surfaces. All right, so what you can do with this video is when you come to a question, you can pause it and take a look. But I'm not going to stop for a super long time. I'll read the question, but I'll let you pause the question and answer it the best you can. The force of friction can occur. Pick the best answer. The answer is all the above, because with sliding objects, we just discussed that. You have the rough surfaces coming in contact, and water. Water is a fluid that has to move out of the way of an object. It has a property called viscosity. It's thick, it's slushy, so that prevents things from just moving freely without being slowed down. Air is also a fluid. It's not a liquid, but it's a fluid, and it also has some what we call viscosity. You lose viscosity is like basically the thickness of a fluid. So, for example, water has less viscosity than maple syrup. So that's a good example right there. Okay, when Sanjay pushes a refrigerator across the kitchen floor at a constant speed, the force of friction between the refrigerator and the floor is... So go ahead and pick the best one. You can pause it now. Equal and opposite, that's right, so that you need to cancel these out. And basically, so that there is no acceleration. If it was equal to Sanjay's push, then the object would be accelerating because they'd both be pushing in the same direction. Carefully. Okay, here's another one. When Sanjay pushes a refrigerator across the kitchen floor at an increasing speed, the amount of friction between the refrigerator and the floor would be A, less than Sanjay's push because it's accelerating. So if it was, let's look at the wrong answers. Okay, for B, equal to Sanjay's push, that one is actually sort of correct as well, because since you're pushing in the same direction, it would also be accelerating. So B is this is kind of a tricky question. B could have won as well, but definitely not C, because if you had equal and opposite, then the refrigerator is going to be moving or accelerating or not accelerating. It's going to be moving at a steady speed. and more than Sanjay's push, that's not possible. It's not possible to have, well, let's see. If it is possible actually to have friction greater than Sanjay's push, that would mean it would be accelerating in the other direction or slowing down. So I've got to be careful when I go through these and think about these and make sure that I'm being completely correct. So that's the explanation for that one. And a concept that comes up here that I want to address is called static and dynamic equilibrium. And we mentioned it before. Static equilibrium is where the thing is not moving and it's not accelerating. Dynamic equilibrium is where the thing is moving but it's not accelerating. And as far as the physics is concerned, they're equivalent situations. Because remember what I talked about, like whether something is moving or not is completely relative. Like, so, you could be measuring it from another frame of reference that's moving at a steady speed, then it's moving. But if you're measuring an object and you're in the same reference, then it's stationary. But if you do physics in either frame, you're going to get the same result. So just want to clarify that. So that's why it doesn't matter if something is moving as long as it's not accelerating. The physics is the same. Okay, so mass is basically a property of matter, and the most simple way to think about it is its ability to resist change in velocity. So something has a big mass, it takes a big force to change its velocity. If it's a small mass, it takes a small force to change its velocity, and that's all you need to know about mass. All right, so it's basically proportional to the inertia of an object. So the greater the mass, the more inertia it has. It's also proportional to the weight, but the two are not the same thing. You measure mass correctly with a balance beam. And the way that a good way to kind of think about this in your mind is if you went to the moon and used a balance beam, and you were comparing two masses, mass 1 and mass 2 are going to be the same on Earth, and on a balance beam. If you take it up to the moon, if they're the same on Earth, they're going to be the same on the moon, and they're going to balance out. Now, weight is usually measured with the spring scale. So if you think about that, if you measured something with the spring scale, you're measuring the force due to gravity. So if you took that same mass and took it to the moon, that spring wouldn't stretch as much and it would read less on the scale. And the moon's gravity is 1/6 of that of the Earth. So that kind of gives you an idea how your weight would be compared to the Earth. So if you weighed 120 pounds, you're going to weigh, you're going to only weigh 20 pounds on the moon. All right, so let's go ahead and check, you guys. If the mass of an object is halved, then the weight of the object is what? Halved, because it's proportional. Okay, and we talked about this, so I'm going to go ahead and skip that. So another thing too, one little comment I'll make is weight in metric units, in the units that we use in this class, is in newtons, because remember, weight is a force. Mass is a quantity of matter, and the metric unit for mass is kilograms. Now we do have mass in English units, but it's rarely used. It's called a slug. And it turns out that you can find the pounds by multiplying a slug by the acceleration of gravity. So one slug weighs 32 pounds because the acceleration of gravity is 32 feet per second squared. Now we talked about this in metric terms, that it was 9.8 meters per second squared. Well, that's because you're using the metric system. But if you were to find the Earth's gravity, the acceleration due to Earth's gravity in English units, it would be 32 feet per second squared. Okay, I love this question. Okay, when a string is pulled down slowly, the top string breaks, which best illustrates? A, the weight of the ball, because now you have the force of the weight and the force of the string below acting on the string on top. Since the string, both strings have the same tensile strength, that means that their resistance to breaking when you pull them apart. The string on the top is going to break because it has more force acting. It doesn't just have the weight of the bob there, it also has the weight of the other string, or the force of the other string pulling down. Okay. Second question, when the string is pulled down quickly, the bottom string breaks. Which best illustrates? B, the mass of the ball. That is because the inertia of the ball prevents it from transferring that force to the top string. If you pull it really fast, it's like, if you ever seen that trick where you basically have a tablecloth and the whole table placed with silverware and forks and knives and plates and everything, and someone just comes and yanks the tablecloth out from under all the silverware and it stays put. Would that work if you pulled it slowly? Absolutely not. Everything would come crashing to the floor. The reason why it works is because you rip it out really fast, and the force isn't acting on those objects long enough for them to start moving. Okay. So acceleration is proportional or inversely proportional to mass. So if you make, let's see if I can get a pointer here. If you make the mass bigger, you're going to make the acceleration smaller for the same force. So let's put that, we're going to put that to some questions here in a minute. This Isaac Newton was the first to connect the concepts of force and mass to produce acceleration. So he was the first one to recognize if you put a greater force, if you double the force on the same object, you're going to have double the acceleration. Okay, Newton's second law. We'll read it together. It says Newton's second law, the law of acceleration, relates to acceleration and force. It says the acceleration produced by a net force on an object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. Okay, what does that mean? Okay, what is a net force, first of all? We need to look at the word net. Net means leftover. So when you take all the forces acting on that object from the outside and you add them all up, then what is left over is going to be the net force. It's kind of like your net pay. After you get a gross pay from your employer, but then the government takes taxes, and what's left over is called the net pay. So in the same sense here, what's left over from all the forces pointing in different directions, some are going to cancel out, maybe some will add up. That force is the net force. And the stronger that force, the greater the acceleration for the given amount of mass. And that acceleration will be in the direction that that leftover force is pointing. Okay. So there's the full equation. Is acceleration equals net force divided by mass. Or another way to put it is force is equal to mass times acceleration is equal to the sum of all the forces. Okay, so here we go. So the force in the hand accelerates the brick. Twice as much force produces twice the acceleration. Twice the force on twice the mass gives you the same acceleration as that first scenario right there at the top left. Now let's look at another situation. The force of the hand accelerates the brick. The same force accelerates two bricks half as much. So if you add the mass you double the mass, but you have the same force, then the acceleration is going to be half, because now you have all this mass to move. And that makes sense. And there's a good question that goes along with this, is if you had a 200 ton block of bricks that are on wheels, and they're on a track that is perfectly level and has zero friction, could you get that pile of bricks to a full running speed? And the answer to that question is yes. The thing is, it's going to take a really long time for you to do that. You're going to have to push and push and push. But if there's no friction, it's going to start rolling. And it's going to keep rolling once you get it moving. So eventually, if you keep working at it, you're going to be able to be running alongside this thing, pushing it along on the track. So the only limit is the amount of time that you have to push on it. So moving down to the next part, it says 3 bricks is third as much acceleration. All right, consider a cart pushed along a track with a certain force. If the force remains the same while the mass of the cart decreases to half, the acceleration of the cart is going to do what? Pick the best answer. It's going to double. That's because you're doubling the force, and since force is proportional to acceleration, you double the force, you're going to double the acceleration. And also, if you take away the mass, if you reduce the mass, that means it's going to be easier to push along, and that will also double the acceleration of the cart. Okay, so here's that same question again. It says push a cart along a track so twice as much net force acts on it. If the acceleration remains the same, what is the reasonable explanation? That's right, the mass of the cart doubled when the net force doubled. Because you added more mass and you added the same amount of extra force, the two just cancel each other out. Okay, so this takes us back to that demonstration that I had in class where they dropped the bowling ball and the feather, and we saw that in a vacuum that the acceleration for the bowling ball and the acceleration for the feather were identical. And that seems counterintuitive because you think that, well, isn't Earth pulling the bowling ball faster? It is, but it also has more inertia, so the two exactly cancel each other out. So if you look at the equations here on the right side of the slide, it says force equals mass times the acceleration of gravity, or force divided by the mass equals the acceleration of gravity. Well, if you have twice the force and twice the mass, guess what? The two twos cancel each other out. So it ends up just having the exact same acceleration. At one instant, an object in free fall has a speed of 40 meters per second. Its speed 1 second later is what? Pick the best answer. That's correct, 50 meters per second. That's because, remember, as time goes on, for every second you add an approximately 10 meters per second for every second. So another second beyond this would increase to 60 and 70 and so on and so forth. A 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest. For negligible air resistance, the acceleration of the heavier ball will be, you should have picked the same. A 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest. When the free falling 5 kilogram ball reaches a speed of 10 meters per second, the speed of the free falling 10 kilogram ball is b. It should also be 10 meters per second because their acceleration is the same. Okay, non-free fall. When an object falls down in air, that's not the only force that's acting on it. Remember, we talked about viscous fluids and the air being a viscous fluid. There's going to be some resistance and some reverse force pushing back on the object in free fall. And they're going to partially cancel out. Eventually, as the rock, in this case, or a sack of potatoes, whatever it is, gets faster and faster, the force that's pushing back is going to get closer and closer to the force of gravity. Eventually, the force of gravity and the friction force are going to equal each other, and at that speed, we call that terminal velocity. It can't go any faster because it's rushing so fast through the air that the force pushing back up is canceling the force of gravity. And so this depends on frontal surface area. This is also the more technical term is called cross-sectional area, and also the speed. How fast is it falling? That's how we figure out what the force of air is acting on, air friction is acting on the object. And we talked about this, so I'm going to move past it. And we talked about terminal speed. That's when the air friction and the weight cancel each other out. No more acceleration. It's just going to fall at a steady speed. For humans, that depends on what you're doing. If you're in a dive position, I think it's about 200 miles an hour. And if you're flat, like your arms spread out, I think it's about 160 miles an hour. So this is not free fall. Okay. When a 20 Newton falling object encounters 5 newtons of air resistance, its acceleration of fall is A. It has to be less than G, because it can't be G, because you would have to cancel out, or you couldn't have any air resistance for it to be G, so it's always going to be less than G if that's the only forces acting on it of gravity, and you include friction. So if a person that weighs 50 newtons is to fall at terminal speed, the air resistance needed is, pick the best answer, 50 newtons, because they have to cancel each other out. So it's in the state of dynamic equilibrium, where it's moving, but all the forces acting on the object are canceling each other out. As the skydiver falls faster and faster through the air resistance, that's correct, A, increases. As a skydiver continues to fall faster and faster through the air, the net force, this is a trickier one, B, decreases. That's because you have the resistance force canceling out the force of gravity, and the net force is the leftover is getting smaller and smaller. As the skydiver continues to fall faster and faster through the air, her acceleration is going to decrease. The reason why her acceleration decreases is because her net force is decreasing, because the resistance is fighting more and more of the force of gravity. Consider a heavy and light person jumping together with the same size parachute from the same altitude. Who will reach the ground first? That's correct. The heavy person, that's because the resistance is the same for both, because they have the same size parachute. But the heavier person has more gravitational force. So it's not the same situation when you include air resistance. And we saw that with the bowling ball and the feather. When you drop the bowling ball and the feather in real air, the feather obviously went slower, not because gravity was acting on it in a different way, but it's because the air resistance, the amount of surface areas of the feather is similar to that of the bowling ball, yet the weight is much, much, much less. And we talked about this. This was the demonstration in the hangar where they dropped the feather and the bowling ball. So just think back about that. If you take away the air, they're both going to fall at the same rate. When air is removed by a vacuum pump, the coin and the feather activity is repeated. What's the correct answer? You got it. C. They both happen at the same time. All right, that's it. Hope you guys enjoyed that.